All right, I have the privilege of presenting our next speaker. You'll have to forgive me, my Dutch is a bit rusty. So, Luite Stegeman, he is the author of the GHCJS project and a member of the Core Libraries Committee for Haskell. So, Luite, take it away.
Would you pronounce your own name?
Right.
In the chat room, you know, like.
Okay, the correct pronunciation is Luite.
Doing it all.
That's what I said.
Sort of. I promised that I'd accept his pronunciation, but it's a bit hard. The vowel is weird. It's Dutch, but so yeah, Dutch has these weird vowels that no other language has, and people think I'm good at compilers since I know how to pronounce things like the Brown index and things. So it's only natural that I started working on this GHCJS project. Is the recording working?
Yep.
Great. So my talk is called Fun with GHCJSi, which is the same title as the Compose conference talk that I gave last month. So anyone who's been there probably will not be all that much new material, but enjoy your meal. Let's see. The problem that we have with today's web applications is, I think, familiar to anyone who's been writing things. Browsers only support JavaScript, and if we are used to Haskell with its static types and safety, using JavaScript just becomes a bit unmanageable, or at least we have to think more and fix more bugs. It's more work. So what we can do is, rather than writing the JavaScript ourselves, don't write the JavaScript, but have some automated process to generate the JavaScript for us. And of course, everyone, I guess, here has an idea of what GHCJS does. It takes Haskell using GHC and translates that to JavaScript. So there we get the safety from our Haskell types and the usability in the browser that we are looking for. So GHCJS is based on GHC, but it's a standalone project. So for those who haven't installed it, you can Cabal install it from GitHub, or there's a stack installation thing which is a bit easier on Windows in particular. And you get this.
Comfortable holding the microphone?
Okay.
I'm better closer to you.
Okay, sorry. Okay, it's better? Great.
Yeah.
What GHCJS does is it takes the GHC front end, and the front end parses Haskell, it type checks the Haskell, desugars it, and GHC desugars it into core. The optimizer rewrites core into something hopefully a bit faster. Does all the specialization, inlining, and other things there. You have the core-to-core plugins that do custom optimizations. After that, there's STG for spineless tackless G-machine, which is very close to core in a particular format. And GHC then translates this thing to CMM, C-, which is a cross-platform or platform-independent assembly language, and then generates machine code optionally through LLVM. GHCJS uses the first few stages. It takes up to STG, but after STG it uses its own intermediate language, JMacro, from the JMacro package on Hackage, which is fairly simple JavaScript AST language. It has its own optimizer on the JMacro language, and eventually pretty-prints the result to JavaScript. Since everything after STG is sort of custom, GHCJS doesn't use the standard object files, but it has its own intermediate object formats, and it has its own linker that compiles, just like GHC, split object style linker, everything that the program needs to run the main action. So it starts at main and it collects the functions reachable from there. And even if you have a very big library that you or packages that you link, if you only link in need a very small part, GHCJS will be smart about it and just include the bits that are actually needed in the results. In the end, you get something similar to an executable that you'd run with GHC. Well, installation, I introduced it already. You can Cabal install snapshots. You can also get things from GitHub, but you need to do a bit more preparation. And the easiest way to get started these days is probably, if you're used to Nix, use the package Nix distributions, or to use the stack tool to set up the compiler. And in particular on Windows, since you need some build environment to build the whole thing. So GHCJS is based on GHC. It's installed as a separate package. You get a GHCJS program rather than GHC. But still, it's not just a one-way thing. Some of the changes that GHCJS needs have been upstreamed in GHC a few years ago, and the most important ones at first were some improvements in cross-compilation, since the JavaScript target is kind of specific backend. JavaScript numbers don't have enough range to be 64-bit ints. You can efficiently do 32-bit integer arithmetic in JavaScript. So we treat JavaScript as a 32-bit platform. And a few other things. And all those, the platform in this sense can be different from the host platform if you have 64-bit GHC. So some changes were made in GHC to allow these things to be set dynamically, so you can build your own cross-compiler as a separate package. Another thing is API hooks that are in the module hooks in the GHC package. And that allow parts of the GHC pipeline to be replaced or changed by programs that use the GHC API, and that's what GHCJS uses to take over after the SDT phase. But also for some things like template Haskell. For template Haskell, some code needs to be run during compilation, and GHC used to load the code directly in the GHC interpreter in the same process as GHC, and it would the result of the template Haskell code would be some Haskell AST that would be spliced into the compiled code, and GHC would continue running compiling the module that it's working on. One of the improvements from GHCJS that now made it into GHC 8 is external interpreter template Haskell that's also used for GHCI. Since GHCJS, since I think 2 years ago, runs template Haskell not by loading things in its own interpreter, since it can't. All packages that are not the package that it's currently compiling are saved to disk as well. Archive files, and there's some intermediate JavaScript code.
Sorry, it died.
Oh, it died. Okay, so there's some. So GHCJS has JavaScript code for it. So the only way it can run the code that it's working on with template Haskell is by loading this code in a JavaScript environment. So GHCJS has been using Node.js, sent the code over there, run the code, and it has some wire protocol to request more information from the compiler. Sometimes you can, for example, in your template Haskell code, request all the classes that a particular type implements, or other things. You can reify a name and get some information on the name. So there's some communication between the browser, or not the browser, between the compiler and the runtime environment. Simon Marlowe took this code since he wanted GHCI to produce stack traces. And GHCI could, in theory, already produce stack traces, but in Haskell, or in GHC Haskell at least, stack traces depend on the profiling infrastructure, which means your code annotated with profiling. Okay, thanks. So if you compile your code for profiling, there's all kinds of profiling instrumentation that keeps track of the cost center that some code is working on, and that's used to reconstruct call stacks. And you could, in theory, recompile the whole of GHC with profiling and have call stacks, but that makes the program rather slow. And the problem with loading your template Haskell or interpreted code in the GHC process is that it's running under the same Haskell runtime, and there's a mismatch here. If you want profiled code or want to run profiled code, you need the profiled runtime. If your compiler is not profiled, then your compiled code has to run in that same runtime. So what GHC8 introduces is the same thing. We just move our compiled or interpreted code to a separate process. We communicate with that process over some socket, and that's how we can have different runtime, profiled runtime in one place, and compiler still fast and profiled code. And that's exactly part of the code for this is exactly the GHCJS template Haskell code. So I hope in the future we'll have more things that can improve things. But these are some of the things that have made it into GHC. Well, this is the architecture of the external interpreter. The GHCJS and GHCJSi architecture runs on Node.js. So if you compile template Haskell, your GHCJS compiler will start in the background a Node.js process, and it runs the template Haskell code on there, and it gets the result back, and it finishes compiling. GHCJSi is a newer thing, but it's based on the same architecture. If you run your GHCJS REPL, your code will be run in a JavaScript environment. So all the Haskell code that you run in GHCJSi has access to the same JavaScript interaction things that you have with regular GHCJS code. So all the Haskell that you can compile with GHCJS is just regular Haskell, but there's one main extension, and that's for an import JavaScript, which allows you to communicate directly with JavaScript things. It has placeholder syntax based on UHC and Fay, where you can directly import JavaScript patterns and do things with the Node.js environment or in the browser, depending on where you run your JavaScript. So if you run your REPL, then the user interface looks just like GHCI. You get a terminal and you get a prompt, and you can immediately run your code. But the cool thing is, and I'm going to show that off later, but I'm spoiling it now. If you want to run your code in the browser, then you can connect your browser to your GHCI session, and you can immediately and interactively access everything in the browser from your REPL. It's still your command line or your prompt, your REPL, is still a separate terminal window, but all the code is just shipped over to the browser to run, and you can do, I think, pretty cool things with this. Earlier this week, I merged GHCJSi in the master branch of GHCJS. So if you just get something from the latest snapshots, then you will automatically get the REPL itself. It's a fairly new thing, so there's still some polishing to do, and I think mainly with GHC8 and later I'm going to work on better integration between the GHC code and the GHCJSi code, since there's a lot of copy-paste going on. But the main other project that I'm working on at the moment is the code generator, since and it hasn't had very much attention in the last year. Since last year I mostly worked on the standard library and stabilizing the compiler itself. But I'm not completely satisfied with the performance and the code size that you get from GHCJS. And there are some new features in JavaScript in ES 2015. It used to be called ES6. But the main thing is tail calls, and tail calls in JavaScript just mean that if you have a function call in specific positions, then the JavaScript environment is not allowed to grow the call stack. You can indefinitely tail call functions rather without ever blowing the stack, and that's something that's potentially very useful for improving performance of the code compiled by GHCJS, since Haskell is, if you compile it, is very tail call heavy. So that requires a bunch of infrastructure changes in the code generator to make sure that we can target or can make use of these new features while still keep it possible to run the code on platforms that don't support this yet. V8 already has native support for tail calls. I don't think it's in Chrome yet, but it looks like it's coming to the latest version of the modern browsers very soon. So I'm hoping to have some results later this year with improved modern JavaScript platforms. In terms of code size and optimization, I think it may be needed to briefly fork the GHC compiler to a private package that GHCJS will depend on to change how the optimizer works and to change the information that we can use from GHCJS. But that's probably something that won't be very noticeable for most users. But it's something where I'd like to just do more, be able to change more in GHC than just use it. But that's just what I'm working on at the moment. So if anyone's interested, just ask me later. Well, like I said, the compiler is a separate program, and you just invoke it like normal GHC, and the code that you get runs in the browser. That's the main target, but it's also usable as self-contained Node programs. So some people have been using this for replacing Perl or Bash scripts. You can write things in Haskell, and if you have Node.js on the system, then things just work. And of course, Cabal and Stack and stuff, they're all supported by GHCJS. And what you get is a complete Haskell runtime. It has concurrency, it has mVars, lightweight threads, SVM. They're all implemented in JavaScript, so if you're interested, the implementation is a bit simpler than in GHC, so it's actually, I think in a sense, sometimes a good introduction to how these things are implemented. JavaScript by itself is single-threaded, so everything is lightweight threads and things on top of JavaScript. This makes the implementation a bit simpler, so since we don't need a low-level locking that the concurrent GHC runtime needs, since there's really only one JavaScript thread running at the same time. On top of this standard Haskell I mentioned before, you get for an import JavaScript a low-level mechanism to directly talk to JavaScript, but there are also some libraries available to make it easier to, for example, work with the DOM. The GHCJS DOM library is a complete generated binding for the DOM API that you can access in the browser, but it's cross-platform, so if you use GHCJS DOM in a native application, since it's also usable there, then you can talk to a DOM if inside, for example, WebKit HTML renderer. So you can still use DOM there. There's also GHCJS FFIQQ, which is a quasi-quoter for more convenient notation of inline foreign imports, but it just uses a combination of quasi-quotation and automatic generation of the foreign import JavaScript things through template Haskell to generate the code. So, I said that running Haskell is one of the main points, and when I switched to this next slide, it was actually doing this. This thread is based on an inline block of Haskell. My whole talk is a markdown file processed by Pandoc with a Reveal.js backend, and I have some Pandoc document processing thing that takes some code blocks and adds some interesting things. So normally when you have a Haskell code block, it will highlight it as Haskell code, and I've added here that if you say my block is a run Haskell block, then it does the same. It includes the highlighted code on the page, but it also ships the code to GHCJS, compiles it, and inserts the JavaScript in the presentation. And when switching to the slides, it calls some function to do something. And in this case, my function that function gets an element that's on the same slide as the code block. And in this case, this thing started 10,000 threads when I switched to the slide. Each of these threads sleeps for a random amount of time and changes one of these table cell colors randomly to something else, and then keeps looping that. So when I switch away from this thing, it kills 10,000 threads. When I switch to this, it starts 10,000 threads. And it's just pandoc and all Haskell. It's really convenient to work with. There are more interesting things than just starting threads like this. For example, if you use the lens library and you thought, hey, the Pong game is an interesting example, you just cabal install lens and you include some lens files and you can play Pong while you're giving a talk. So this uses the gloss backend, and it starts this thing when I switch to the slide, and it stops it when I switch away. So this, well, I think a fun use case of GHCJS. With GHC, these both things use lightweight threads to start something when the slide started, when I switched to the slide, and stop the same thing when I switched away from the slide. The REPL GHCJSi also works with lightweight threads. If you have some short-running computation, then you will immediately be dropped back to the prompt, just like in GHCI. If you have simple computation, you get the answer and you enter something new. When you have something that runs longer, then there's a foreground thread running, and that keeps your computation busy. You won't get the prompt. But just like in GHCI, in GHCJSi, when you press Ctrl+C, you abort the current computation, and the runtime system sends an exception to the foreground thread. That thing tries to abort your running computation and falls back to the prompt. But you have the option to handle exceptions there, and that's something that's useful in GHCJSi, in particular if you use the browser front end to work with the document or work with animations or have more interesting results than just some text output. So I'd like to show that it works. It does. GHCJS doesn't ship with a wrapper script, so you can use Cabal Rental or just GHCJS _ interactive, and it will start your GHCJSi session. If I'd enter an expression now, then it would run it directly in the Node.js environment. I don't need anything else, but it gets more interesting if you use a browser. So what I can do is go to port 6400 on localhost, that's the port it listens on, and now my GHCJSi said that my code is going to run in the browser. So if I type something simple, well, that's not what I want, then the first time it takes a while to compile. Since it compiles the expression, then the GHCJS linker collects all the dependencies of this expression, which in this case, since it's the first one, includes the whole runtime system, parts of the base library, which includes character encoding and buffering and all these things. So that takes some time, but it remembers what's already in the JavaScript runtime. So if I do some other computation, now it's much faster. It compiled this thing, it figured out that most of the JavaScript code was already there, so it sent up a tiny bit of JavaScript to the browser and ran that, and that's how it gets this result. Let's see, I forgot to load my demo file, so yes. So now I have my some demo file loaded. I think you get with sorry. So all the normal GHCJS, GHCI commands work. So I can browse and see that I have a whole bunch of things loaded. I think I have something like table. Does this work? Yes. So I have something that adds some table to the document, and I can do more interesting things like does this work? Yeah, something like this. And I have a few other functions like, well, this is just clearing the thing. And the code is pretty simple. It just uses very low-level foreign function JavaScript imports. Let's switch back. And I have a few other things. For example, there's a gloss backend, and that's so I can do something like I have an animate function that takes gloss animations with our functions from time to some picture. And I have something like square, which is something that's just a constant function of, this is a black thing, so now I can actually see the square. And since we're dealing with time functions, I have other things that make it more interesting. So now I have a rotating square. And I have, let's see, call grid, yes, tab completion works. I think this does multiple squares, so just with some color gradients, I can make them rotate again. And well, I can rotate the whole thing again if I don't. Yes, so something like this. And the last zoom funky effect is this. And this is just a gloss backend. And I've used this a whole bunch of times, but the way this works is, as you can see, I entered here this expression and it keeps my computation going. There's a foreground thread going on, and all the time, even though it's not quite handled correctly, like it prints a loop exception, which is non-termination, it shouldn't. So GHCJSi is not quite stable yet, but it's still quite usable. But it needs some polish. But this foreground thread is running, so the gloss event loop that just recomputes this picture in, I think, request animation frame loop, so it makes it relatively smooth, a bit smoother if I'm not recording the screen. This adds this canvas to the document when I start this computation, and every time I press Ctrl+C, it removes the whole thing from the canvas again, in exactly the way that I told you before when I mentioned exception handling and how GHCJSi works. So my animate function that I keep calling is here. It just is a bracket. When I start the animation, it clears the body, so I have nothing in the document left. When it stops, or finally after I interrupt the animation with Ctrl+C, it clears the body again, so it just makes blank the document. And in between, it calls the gloss animate function that will keep just running in the current thread. If I wanted to interact with animations, or keep an animation running and do other computation at the same time, I could do exactly the same, or I could do exactly what I'd expect, what you might expect. Like this is foreground, and I think this would be a background thing, but so now I have my thread back. Unfortunately, since I didn't save the thread ID to a local name, I can't kill this thread anymore. So you have to be a bit careful. But if you just work with, or if you're familiar with working with threads and Haskell, you can use all these things in the way that you use normal Haskell. And I think it's a pretty powerful way to make this kind of Haskell sessions more directly interactive. So that's, yes?
What's the URL you put in the browser? What was the port?
The port number is 6400. I think there's Yeah, I think there's an environment variable or something that lets you change the port that GHCJSi works on. And you need the socket.io library for Node.js installed to make this connection work. So let's get back to the rest of the slide, or the conclusion. The whole REPL is actually has been only about a week of work to implement, and the reason is that everything is more or less based on existing infrastructure. Running or linking Haskell incrementally, just including things that aren't already there. That's something that I already did for template Haskell. And all the other things that I showed are really not magic at all. They're lightweight threads. You do some exception handling. You use bracket, fork.io and things, and maybe you bind things to local names. And all the GHCI sessions things that you might be used to, they work exactly the same in GHCJSi. The only difference is that you have access to foreign import JavaScript, and that gives you access to browsers directly. So that's pretty much what I wanted to show. So if anyone has questions, then please.
How does the gloss, can you talk more about the gloss backend to, how it gets into the browser, basically?
Right, so the question is, how does the Gloss backend get into the browser? Gloss is a 2D, mostly vector graphics drawing library, and it's based on OpenGL for native code. I have an experimental GHCJS backend that's still not published yet.
Is it up on GitHub or no?
No, that's what I meant.
Okay.
It's
Okay.
not quite complete, but I think I should publish it soon. The Gloss backend draws on a canvas, and it uses the request animation loop to get you smooth animation, and that's basically it. And the thing that's currently missing, and why I've not published it yet, is that it should be able to load bitmaps, but that part is not quite ready. Plus, the Gloss library hasn't really been designed with this kind of non-OpenGL backends in mind, so the code is a bit hacky, and maybe if someone would like to help properly integrate it into Gloss, that could be a fun project to work on.
Could you show any example code of integrating with an existing JavaScript library?
Well, my demo code doesn't really integrate with a particular library, but it does show some, or it does use some built-in JavaScript things. So on the left, I hope everyone can read it. There are a few foreign import JavaScript statements. Well, this is my... so here's something that gets the current document body from the browser. So document is a global variable that has this body property. That's not pure since it can change, so it's an I/O thing. And JSFL is the low-level primitive for GHCJS that can contain any JavaScript value. I've been using that sort of out of convenience with these things, but in the GHCJS base library there are more high-level new type specializations of these things, like specific JavaScript variables that are always an array or a specific object, and you can do more things with that. But the basic thing is always something like for an import JavaScript, you have a bit of JavaScript code with the placeholders. $1 is the first argument, like here. And that's how you set up all your calls with JavaScript. And the GHCJS base library has some examples for bindings for XML HTTP requests, and I think, let's see, WebSocket, I think too, typed arrays, non-typed arrays, that kind of thing. So there's a whole bunch of examples there, and there are some other bindings for more complicated libraries.
What does it look like going the other direction, having JavaScript call your GHCS code? GHCJS.
The easiest way of calling from JavaScript into GHCJS is by starting the Haskell program from the main action and using the for an export code from the GHCJS base library to get some JavaScript values that call or run some Haskell action internally if you call them from JavaScript. Yeah?
So can you talk about the granularity for how the statements are interleaved with the different threads? So normally in JavaScript, the function has to run to completion before it's released back to before the loop considers one or the different functions. So GHCJS, does the granularity happen in each expression as its failure, or does it have to complete a full function call before it considers the different threads?
Right, so the question is about the granularity of the threading. So let's see, the granularity is really small actually, since most of the Haskell code is something that does a tail call to something else, and JavaScript currently does not have tail calls by itself, and as long as you don't know how much time something how many calls deep something will go, you might at some point blow the stack. So the calling convention for GHCJS is rather than tail calling something, returning the function to call and setting some global variables to the arguments that you pass. So for all tail calls, you fall back to the main loop, which controls the threading. That thing has a limited number of calls that it does before it checks the amount of time that has passed since starting the thread, and if that's more than the time slice that you're working on, then it will switch back to the scheduler, and if there are other threads that should be run, it will run those. If there are no other threads, it will just continue, and sometimes it will fall completely back to the browser to let it redraw the user interface or handle events or something. It depends on whether you're in an animation frame loop, then it won't do that, but there are a few configuration options for those.
Does that work even if you call into JavaScript?
No.
Okay.
So the Haskell threading only works inside the code generated by GHCJS, and if you want your threading to continue to work, all foreign calls to JavaScript should be considered something similar to unsafe C calls in the native Haskell code. They block the whole Haskell runtime, so it's probably best to make them short. And there's one example in the GHCJS VDOM library where the diffing code between virtual DOM trees is done in such a way that the amount of work that's done in one particular point of time is fairly small, and it returns more work to the Haskell runtime to continue rather than keeping the JavaScript interpreter busy. Sure.
You mentioned that right now the preferred way to get a pointer to a Haskell value that you could send to JavaScript like a function is using the foreign export. With the CFFI, there's a way to generate a wrapper, which is like a function pointer to a Haskell function that you can then pass to C. Have you thought about anything like that so that at runtime you could get a JavaScript function that actually calls back into Haskell?
So the question is there something similar to generating a function pointer with the C call FFI to GHCJS? Actually, what I suggested is exactly that. That's the only mechanism that really works at the moment. So what you do is you have, say, a Haskell I/O action, and you export that, which means you get a JS file, JavaScript value that you can pass to JavaScript over the FFI, and that's a function, or if it's just an I/O action, it's really a function that does not take any arguments, although it can be a function that does take something. And if you run that, then internally some Haskell thread is started and something is done. So for event handlers or something that call back into your Haskell, that's exactly what you'd use there. And it works for any Haskell action. Yeah.
What size does like Hello World compile down to? How much JavaScript? And you said you're working on it, so kind of what's your target?
I think I have to admit that I'm not quite sure of Hello World, but I think it would be like 600-700 kilobytes unminified and a few hundred still minified. That includes the runtime and the base library that's has the buffering things, but only the things that it actually needs. Like I said, it's a split objects linker. I think I should be able to at least half the size, but it's a bit hard to predict here. Most users don't have too much trouble with the code size unless they have a very big project or unless they want to run it on smaller mobile devices. And in particular for those, just extending the range of applications that this stuff can be used for, I'd like to spend some time to make it considerably smaller. I think it can be done, but the current optimizer is really the JMacro intermediate language is completely untyped, and all optimization rules sort of have to guess what the JavaScript is trying to do. There are some annotations, some special variables, but adding better rewrite rules there. It has a data flow analyzer that changes or does constant propagation and removes whatever unnecessary assignments and removes unreachable code paths. But it's really hard to use or add optimization rules or improve the strategy without more information. So that's the first thing that I'm doing. I've already written most of this code, but at the moment I'm mostly busy porting the GHCJS code base to GHC8, and it's a fairly large amount of work. But I want to finish this before GHC8 is out, since even after the first release candidate, they keep changing things at an alarming rate. So yes, it's probably better to make things work first. But it's going to, it should be out there in a few months or something.
Do you?
Sorry, you first.
I'm just going to say a word to the wise. Template Haskell seems to be able to bloat your code size dramatically. We have a big template Haskell generated thing, and my executables went from a megabyte to 12 megabytes in a hurry. So it's a lot of fun when it takes 30 seconds to load your JavaScript in the browser.
Right, yeah, so the risk of doing template Haskell is that it's so easy to generate huge expressions that then the browser or the compiler has to compile down to JavaScript or machine code. That it can really blow up your code size. Plus, this type of code is very repetitive. And I've done some analysis of generated code there. I think by deduplicating all these repetitive parts, it should be possible to get much smaller code in these particular instances. But unfortunately, GHC at the moment doesn't have any infrastructure for improving there. So maybe this is again something that can be started by GHCJS and in the end be merged back upstream into GHC. We'll see.
I think our solution will be to move to generics instead of template Haskell eventually.
Yeah, moving to generics from template Haskell can sometimes be a solution, but often template Haskell code is more performant, or you can specialize the code for the types that you're using. In generics, really, you can only do these sum and product constructor things, and if you really need high performance, sometimes that's hard to get out of that code, even though it's slower.
Do you have any tools you can recommend that we can track through this stuff yet? I mean, how do you start looking at the code load size, I guess?
When you compile a program with GHCJS, one of the you get a directory with a JSX directory with an old JS which you can run with Node.js and an index.html and a few smaller JS files that are the separate parts of the runtime system and stuff. But there's also, I think, an out.stats file, which contains the code size statistics for the out.js file. And the out.js file is the generated code from GHCJS. It doesn't include runtime, but it's just the compiled code, the compiled Haskell. And it includes code size broken down by package and by module name.
It does.
Do you plan on using like JS optimizers at any point? Like having a compile flag or something for calling the closure compiler or something, or like that. I don't know.
So the question is, do I plan on integrating, calling a JavaScript optimizer minifier like closure compiler directly from GHCJS? I think the answer is no. I think the goal is to keep the code compatible with closure compiler. There are annotations for things like constructors in the runtime system code, and most of the time code should work with closure compiler, but I think it's something that's really best done separately from in the build system rather than something that's built into GHCJS itself. The main problem is that GHCJS will have to link all foreign JavaScript code. You can include any JavaScript code from in packages using the JS bits field in Cabal, and that code may or may not be compatible with closure compiler or other middleware options. So it's really something you have to determine on a project-by-project basis. So that's why I think it's not something that GHCJS should do itself. There's one thing that it will do. The new intermediate language and its pretty printer have a minified output option. Currently, it always GHCJS always produces pretty printed output with indentations and line breaks, so it's relatively human readable. But yeah, one of the new things is just fitting as much as possible in one line and making it smallest, so it saves you one step. It's not quite as efficient as say purpose-built JavaScript minifiers, but it gets you most of the way there without having a fairly lengthy extra step in your build process.
Along those lines, have you given any thought to an ASM.js compile target? Do you have any opinions of that?
So ASM.js is a subset of JavaScript, which, well, the guys at Mozilla designed for targeting their LLVM or using mscripting compiler that translates LLVM to JavaScript. So ASM.js is a very small subset of JavaScript that doesn't allow you to do anything that relies on the memory manager. You can't use objects. Everything global is stored in a very large heap array, typed array, which has to be size power of 2. This means that if you use this as a general target for all your Haskell code, everything has to be in there. You can't use any JavaScript objects, and you have to port the storage manager from native GHC to JavaScript and do all the garbage collection in some JavaScript code. At the moment, I don't think it's worth the trouble doing that. I'd like at some point, if they make it possible, to use the WebAssembly project, since that's a binary distribution format for JavaScript. Currently it's limited to the subset that's more or less ASM.js with some extra room for type annotations, but that lets you skip the parsing step, so it lets you start up things, especially on small devices, a bit faster. And that would be useful in general. The only downside is that the WebAssembly project just is targeting the same things, so they've limited this to just the ASM.js subset. So if they extend this to full JavaScript but a binary distribution format for this, I'd say yes, please. Other than that, I think it's better to first focus on optimizing and just improving the compiler in general before spending probably more than a year doing all the low-level storage management by hand in JavaScript. That's it.
So, sort of building off of that, do you ever imagine, instead of going from STG to JMacro, do you ever imagine going from LLVM to JavaScript? Like, basically, instead of writing the JavaScript code, use the LLVM JavaScript or to WebAssembly or JavaScript compiler.
So, if instead of STG we used LLVM as a starting point, then you could, in theory, compile, say, the GHC runtime system to JavaScript with mscript and get everything sort of for free, except that it doesn't really work. Maybe with tail calls we can get further, but at least in older JavaScript versions, you yeah, the code that's Mscripten is based on, since the question then is, well, why don't you just use GHC to compile to LLVM and then use Mscripten to do the last step? I don't think that's really has ever worked. Plus, it makes it way harder to do the JavaScript integration with the foreign import JavaScript things that we have now. That's also the main reason that CMM is not used. CMM is a bit too low level to keep all these things in. Plus, it's like it's assembly, it's unstructured control flow. You have jumps all over the place, and JavaScript doesn't have any way to express these things. So what Mscripten does is it tries to recover these things to normal JavaScript loops, and sometimes it fails and it has to do some weird while and switch combinations that are a bit ugly and a bit slow. I don't want to go through to jump through all of these hoops and lose all the convenience of having relatively high-level JavaScript in the middle. So I don't think it's currently very high priority. It would maybe be possible to make it work, but it's definitely not trivial.
Great, thanks.
Anyone else?
So will any of the network, like HTTP packages package, will those somehow transparently make an HTTP request in the browser, or is all I/O basically an FF and FFI script ahead? So like, or for example, a node reading file, do we have to write a FFI system for that, or with the Haskell reading file?
Right. So the question is whether packages like network or HTTP work in the browser and how they work. The browsers don't support TCP connections. The only thing that you can do from a browser is WebSocket and XML HTTP request, but just raw TCP, they don't allow that. In Node.js, in theory, you could make these things work. The network package has some C FFI that it uses to talk to the underlying socket library of the operating system. And at the moment, there's no GHCJS implementation for those networking things. But it's very similar to, say, the file I/O or sub-processes, child processes. Those things have been implemented for the process package. And that's the implementation mostly consists of things that either implement the SQL FFI by implementing some JavaScript functions that use the SQL calling convention, which is a bit weird, but it allows you to emulate pointers in JavaScript with typed arrays. And many packages, especially with simple things like memcopy or something, you can just write a very simple JavaScript implementation that you drop in place of the C function that's called, and it just works. For the network package, most of the things would probably be implemented that way, and there are a few things where you'd have to do some conditional compilation. One of the main things is the, I think, get host by name call, which is normally as a C function blocking call. With in Node.js you only have a non-blocking call that gets a callback. So if you want to do this, you'd probably have to conditionally compile this to a foreign import JavaScript that does an asynchronous non-blocking call. But it wouldn't be all that hard. There are examples for file I/O and sub-processes that are used, for example, by the Cabal infrastructure. Cabal, when you have a custom setup script, it compiles, if you use GHCJS, it compiles the setup script to JavaScript, and it runs the setup program with Node.js, and Node.js then provides the underlying infrastructure for example, running processes. So your setup script will call GHCJS package, and it will query the GHCJS compiler itself for its version number and the things that it supports. So for those things, it works. It's just a matter of implementing the bindings with the underlying API.
So it sounds like then in the browser, then, like at least as it stands today, you would just try to external FFI. Like XML, you send it to your HTTP call, and then you pass that back into GHCJS.
Well, if you want to do an HTTP request, there's bindings in the GHCJS base library for the XML HTTP request object. But that's a very different API from doing raw socket. If you have, say, a high-level HTTP GET function, or maybe the HTTP library or something, you could conditionally compile that to use GHCJS base if you compile things with GHCJS, and otherwise use the lower-level network package for those things. Any more questions? If not, then thanks for your attention.